Welcome back to our 4-lecture exploration of the remarkable phenomenon of cosmic inflation. In the last lecture, we learned how the early universe might enter a brief phase in which a dense vacuum arose and fell outwards in a brief burst of exponentially accelerating expansion, which launched the standard hot Big Bang universe. And at the same time, it solved the flatness, horizon, and monopole problems that had plagued the normal hot Big Bang story. But remember, there was one more problem needing to be solved, the structure problem. The fact that the universe is neither wildly lumpy nor fatally smooth. But in Goldilocks terms, it's just right. One of the critical challenges facing any cosmological theory is, can it generate the seeds of roughness from which stars and galaxies grow? Now, I'm glad to say that almost as soon as inflation had been introduced, in part to solve the other problems, it was quickly realized that it could also solve the structure problem. In fact, as we'll see, inflation achieves this task so well that most cosmologists now view this as one of inflation's most impressive qualities. So that's the theme for this lecture, inflation's remarkable ability to generate the seeds from which galaxies grow. Now, to see how this might happen, we need to remember what it is that's expanding during inflation. It's a quantum field. And the answer to the source of roughness is in that first word, quantum. It's not an idle word. Now, in classical physics, a field would be completely smooth. But in quantum physics, a field, and in fact pretty much everything, is subject to ceaseless and profoundly random fluctuations. And ultimately, it's these fluctuations that are going to be the source of cosmic roughness. So let's look at this topic of quantum fluctuations in a bit more detail. In our everyday lives, we get the distinct impression that objects are essentially well-defined. They have smooth boundaries, and if left to themselves, they can be perfectly still. Even if we knew they were made of atoms, and these atoms were jostling around, we might still view the atoms as little spheres behaving in a predictable way, bouncing this way and that as they collided with each other. Well, it turns out that this perception of nature is only approximately true. If we were to zoom ever deeper into objects, we'd find a rather different world, one that was much less orderly and precise. It turns out that the bedrock of nature, the cloth out of which everything is woven, has a built-in, ceaseless dynamism. Its constituents are not well defined, and their properties continually vary with a sort of inherent blurriness. Now, this rather unfamiliar behavior of nature is described extremely well by the subjects of quantum mechanics and its close cousin, quantum field theory. You may not know this, but these are in fact the most successful theories that physicists have ever constructed. Not a single experiment has ever disagreed with them. So even if we can't easily intuit this kind of micro world, it really does seem to behave that way. And we should trust what these theories have to say. So let's have a look now at how quantum fluctuations might generate structure during inflation. So the most important thing to recognize is that the energy of all things, including this quantum field, continually fluctuates. Up and down and up and down. Its long-term average looks like the smooth field on the right, but at any instant, the field has some roughness and looks like the region on the left, with very slightly different energy from place to place. Now, we must add to this picture a crucial feature. The region of vacuum is experiencing an accelerating expansion, and this alters the situation in an extremely interesting way. Let's focus on a patch of vacuum and watch its expansion. At some distance, the region's boundary is moving away from its centre faster than the speed of light. Now remember, space itself can move faster than light, it's just that things can't cross space faster than light. Now, the place where this light speed threshold is crossed is called the Hubble sphere. And once it's crossed, the material outside becomes fundamentally disconnected, severed, if you like, from the material inside. Okay, back to our quantum fluctuation. Let's imagine, at one particular moment, the fluctuation makes the energy slightly higher, and while it has that higher value, the region expands through the Hubble sphere, and as it does so, it gets disconnected, and instead of going back down again, gets frozen in. It becomes a real enhancement with higher energy. Let's follow that again with a slightly different diagram. Close to any location, the energy in the quantum field fluctuates randomly. But as soon as the expansion makes the region bigger than the Hubble sphere, the fluctuation no longer oscillates, but freezes at whatever energy it had when it expanded across the threshold. From then on, it's locked in, and the field has a genuinely different energy. Overall then, because of expansion, quantum fluctuations are becoming real fluctuations. Roughness is being created everywhere as regions expand past their Hubble spheres. Well, we're beginning to build up the picture here. So let's make this a bit more quantitative and see if we can span the huge gulf between tiny subatomic quantum fluctuations and enormous galaxies. So let's just choose inflation to occur at 10 to the minus 20 seconds. So the expansion doubling time is also about 10 to the minus 20 seconds. And the Hubble sphere is about 100th of the size of an atom. So quantum fluctuations get frozen at that size. Now let's imagine inflation lasting 40 doubling times. So that tiny region grows by about 2 to the power 40, which makes it about 100 yards across at the end of inflation. Now at that point, normal expansion takes over and makes this region about 1 million light years across today. Now, and this is the crucial point, if the original quantum fluctuation gave a slightly higher vacuum energy, then it will lead to a slightly denser region that over time collapses to become a galaxy. On the other hand, if the original quantum fluctuation gave a slightly lower vacuum energy, it'll lead to a slightly lower density that over time becomes a void or gap between galaxies. So overall, inflation takes a tiny quantum fluctuation, makes it real, and then stretches it to cosmic proportions. Now, so far, I've just described how a single fluctuation might have turned into a single galaxy. But in reality, of course, every location is generating fluctuations. So these figures help show what's going on by following 5 tripling times of a single small region. In this first one, you mainly notice the expansion itself. The initial region is so tiny you can hardly see it, but it grows by a factor of 3 between each step. And by the 5th step, it's grown by 3 to the 5th, or about 200 by 200. And that now fills the whole square. Now, this second set helps us to focus on the growth of roughness by not showing the expansion. We start with our single region of vacuum, filling its tiny Hubble sphere, which here is shown as a square. Now it expands to a 3 by 3 region. Its fluctuations get frozen in, and so these new regions inherit slightly different values of the vacuum energy. But then each of these 9 regions spawns another 3 by 3 set which in turn have slight fluctuations. This repeats and repeats and gradually generates an ever richer pattern of roughness. Notice how the fluctuations build up. For example, a somewhat lower fluctuation entered in the top right of the second step. And so from then on, the top right is always going to be a bit lower, even though later fluctuations introduce additional, finer levels of structure. Now, I hope this last square looks at least vaguely familiar to you. Let me jog your memory with a picture of the microwave background. It's covered with roughness on all scales, from huge regions to small regions, all superposed in a patchwork that looks very similar to the little example I just showed you. Now, you may worry that there's a big gulf between the time of inflation and the time of the microwave background, but that's really not important. Remember that everything on the microwave background larger than about 2 degrees, that's the size of these little circles, has not been in contact since before inflation. So stated slightly differently, those big patterns on the microwave background are exactly as they were at the end of inflation. Nothing's changed. Now, if inflation took place at 10 to the minus 36 seconds, as many cosmologists suspect, then the region we're seeing was about the size of a bacterium at the end of inflation. So the microwave background is giving us a picture of a bacterium-sized piece of the universe when it was only 10 to the minus 36 seconds old. Now do you see why the microwave background image is so profound? It's not just a depiction of a hot glowing fog at 400,000 years. It goes much deeper than that. It connects us almost directly to the era of inflation. It's like a microscope and a time machine rolled into one. It takes us back to the Big Bang's inflationary launch and it photographs it. Now, this is already a stunning realization, but let's continue along this line. Here's another familiar image, a map of the web-like patterns of thousands of galaxies spanning several billion light years. Once again, we should begin to look at this differently. Those mottled patterns were made in the quantum world, down on scales much smaller than an atom. You're seeing a pattern of subatomic quantum fluctuations written across billions of light years using galaxies for ink. These are wonderful examples of the wholeness of nature, the behavior of nature's finest level, the quantum character of the vacuum, helps craft a giant framework for the entire universe. It's the quantum in the cosmic. It's a transcendent idea. Now, at this point, all I've done is to describe how inflation might generate roughness in the universe. I want to spend the rest of this lecture outlining some of the evidence that supports this idea, so you'll understand why cosmologists are becoming more and more confident that this is what actually happened. So first of all, let's look more closely at the type of roughness made by inflation. Does it match what we find for the real universe? Now remember from lecture 17, we learned that there's more to cosmic structure than simply saying the universe is lumpy. There's a size dependence of the lumpiness, which we've been calling the roughness spectrum, or power spectrum to use the proper term. So, it's critical to find out, A, what the roughness spectrum that comes from inflation is, and B, whether that matches what's observed. Now, it turns out that one of the more robust predictions of inflation is a rather specific kind of roughness spectrum. And here's a sketch of it. I'm not going to go into details, but just mention that a pure exponential expansion should give a roughness spectrum that's a straight line with a slope of 1. Density variations increase for smaller regions. That's to the right. Now, let's not forget from lecture 17 that as the universe evolves, the small-scale roughness is suppressed. And so in today's universe, the roughness spectrum looks more like this, with a peak and less roughness on smaller scales. But notice that the primordial spectrum is still present for the larger scales on the left of the peak. Let's now have a look at the observed roughness spectrum for the real universe. We've seen it before in Lecture 17, when we focused on the fact that it had a peak. But here, we're focusing on that part to the left, which hasn't been affected by any suppression, because that gives us the primordial spectrum. As you can see, a slope of 1 does seem to fit the data fairly well. Actually, the situation is much better than it appears, because we know how suppression affects the smaller scales. So in practice, we can fit across the entire roughness spectrum. Here's one of those nice movies made by Max Tegmark that compares a set of models to the microwave background sound spectrum at the top and the galaxy roughness spectrum at the bottom. Now, in this case, the models vary just the slope of the primordial roughness spectrum. And sure enough, the best fit to both data sets gives a value for the slope very close to 1. Now, actually, with more recent data, it's been possible to go one step further. You remember I said that the slope of the roughness spectrum is only exactly 1 if the expansion during inflation is exactly exponential. Well, let's bring back our model of inflation from last lecture. As long as the ball sits at a fixed height on the hill, so the energy density in the vacuum is constant, then we have pure exponential expansion. But when inflation ends and the ball rolls down the hill, the vacuum energy drops, so the rate of expansion slows down. And it turns out that the roughness generated at the end of inflation is a little bit less than it was in the midst of inflation. And what this does is to introduce what cosmologists call tilt, the fact that the slope is slightly less than 1, and also curvature, the fact that the slope curves more to smaller scales. Now, at the present time, that's 2008, tilt has been found. The slope is 0.961 plus or minus 0.014, but curvature hasn't yet been seen. Now, these slight deviations from a simple slope of 1.0 are tremendously important because they tell us about the shape of the hill down which the ball is rolling. And that in turn tells us a great deal about the nature of the scalar quantum field that's driving inflation. See, when you think about it, this is a truly remarkable piece of physics. On the one hand, we have multi-billion-dollar accelerators pushing the study of particle physics to limits near 10 TeV of energy. And on the other hand, we can use the microwave background and its image of inflation to study particle physics at an entirely new realm of energy, 10 to the 12 times higher. It gives us a window on the biggest particle accelerator of them all, the Big Bang itself. There are two more observational fingerprints of inflation that I want to talk about. The first one has been observed, and the second one may be soon. The first goes right to the heart of the nature of quantum fluctuations, and that is their randomness. You see, one of the most puzzling qualities of quantum fluctuations is that they are profoundly random. It's not just that they're very complicated and can't be predicted, like the path of a hurricane. The fluctuation mechanism is inherently random. Not even it knows what it will do next. What that means is that as the fluctuations leave the Hubble sphere, they get frozen at a random part of their cycle. For example, whether they're at their highest or mid or lowest part is random. Physicists say the phase of the fluctuation is random. Now, when the fluctuations are of this kind, with random phases, they're called a Gaussian random field. You may have heard that term Gaussian curve or bell curve. It's a statistical term that incorporates this issue of randomness. So a very important test of inflation is to see whether the observed fluctuations are in fact a Gaussian random field. Now, there are several ways to test this, but a very simple method is the following. Remember, this image of the microwave background is color-coded. Slightly denser regions are in red, slightly less dense regions are in purple, and the mean density is in green. So all you do is to make a histogram of the amount of sky at each density, in other words, at each color. As you can see, the histogram makes a nice Gaussian or bell curve. And this shows that the microwave background is a Gaussian random field. It has exactly the random quality that inflation predicts. Actually, there's a rather interesting consequence of this kind of roughness. It means you will never find any specific shape or image in either the microwave background or the galaxy web. So that metaphor I used back in lecture 16, the microwave background as a primordial document written by nature giving an account of her birth, has a flaw. There could never be any visible script or image. The patterns are profoundly random. But of course, it's exactly that quality, together with the all-important roughness spectrum, that is so revealing. Nature writes her message more subtly than we humans might, without using hieroglyphs or pictures or words. Now, the second observational fingerprint of inflation, which has not yet been observed, are gravity waves. See, when inflation's occurring, it doesn't just make fluctuations in the density of the vacuum, it also sends out ripples in space-time itself. Inflation sort of grabs hold of space and shakes it. Now, these ripples are called gravity waves because, remember, in Einstein's view, gravity arises from space-time being curved, and so a wave-like ripple in space-time is also a wave-like ripple in gravity, hence gravity waves. Now, it's actually possible to detect these gravity waves by, as you might guess, carefully studying the microwave background. Now, this time it's not the patchiness itself, it's another quality we've not yet talked about called polarization. Do you know when you look at a blue sky through Polaroid sunglasses and then tilt your head from one side to another, the sky seems to change? That's because the light scattered from the atmosphere is partly polarized, meaning the light vibrations tend to be in a specific direction. For example, more wiggle up and down than wiggle side to side. The Polaroid sunglasses only let light wiggling up and down through, so how much light you see depends on the orientation of the glasses. Now, the same thing can happen with the microwave background sky. The light from the glowing fog can be slightly polarized, and that polarization is preserved as the light crosses the universe and arrives as microwaves. Now, the microwave telescopes that are used have the equivalent of Polaroid lenses, so they can see if the microwave sky is polarized. This sketch illustrates a pattern, highly exaggerated, showing the direction of microwave wiggles. But in truth, the amount of polarization is very slight and the patterns very complex. But there is a particular pattern, shown here, that is only produced by gravity waves. It's called a B-mode pattern, for reasons I don't want to go into. The wiggle directions make a kind of spiral, and they're a clear signature of gravity waves moving through the foggy gas just as the microwave background was being formed. Now currently, as of 2008, these B-mode polarization patterns are still too weak to be seen, but the hunt is on, and there is great hope that the next satellite to map the microwave background, called the Planck satellite, will soon find them. Now, it's hard to overstate the importance of that discovery if it comes. In many ways, it would do for the theory of inflation what discovering the microwave background did for the theory of the hot Big Bang. It would change its status from being a very promising idea to a very likely reality. Now, I want to end this lecture on an acoustic note. You see, with all this talk of making roughness, let's not forget that we're setting the stage for all those acoustic vibrations that go on in the first 400,000 years. Remember from lecture 15, we can think of all the density peaks and troughs as a whole register of organ pipes. And as time passes and the horizon expands, gradually, starting with the smallest pipes, they start sounding as gas falls in and bounces out, making roughly spherical sound waves. But what inflation does is it makes the entire set of organ pipes, with all the notes ready and waiting to be played. In a sense, you can think of that initial roughness, as an initial set of organ pipes. They hold a latent sound, a silent sound. It's just waiting to unfold given time. So why don't we do what nature can't do? Let's cheat time and play the entire register all at once to see what it sounded like. Here's its spectrum. It's a straight line with a slope of 1. And this is what it sounds like. It's pure noise. It contains the deepest notes and the highest notes. It's like having an infinite piano keyboard, and with flat arms, you press all the notes down together. Now, I know this doesn't sound musically very majestic, but the role it plays in the universe is utterly majestic. See, what this sound is doing is, in a sense, it's shaking the universe's contents with all possible frequencies. And just like a violin bow slipping across the strings shakes the string and the violin with all possible frequencies, only the natural resonant frequencies of the string and the violin emerge as music. With the universe, the dark matter, the atomic matter, and the radiation all respond differently to that initial primordial shaking, and over time, their own sounds emerge. So here, at 400,000 years, are the sound spectra and sounds of how the dark matter and atomic matter have responded to that initial stimulus from inflation. Remember, they've been shifted up by the usual 50 octaves to put them into the human audible range. Those sounds are what lay the foundations for building all the stars and galaxies. So no, the primordial sound isn't music to our ears, but the symphony it started is still being played out across the sky and down here with you and me. Let me briefly review. In this lecture, we've looked at how inflation might solve the structure problem, why the contents of the universe are spread about slightly unevenly. We've seen that during inflation, tiny quantum mechanical fluctuations can get frozen as real fluctuations when they expand faster than light away from their place of origin. The expansion then stretches these fluctuations to cosmic proportions. When you allow for the fact that fluctuations are created at all locations and throughout inflation, you end up with a pattern of roughness that amazingly matches what we find both in the microwave background and in the distribution of galaxies. It has the correct roughness spectrum, and it has the quality of randomness we expect from a quantum mechanical process. With these basic matches between the observations and theory in place, the hunt is now on for more subtle features that can really test or refute the theory of inflation. The roughness spectrum may tilt and curve just slightly in response to the slowdown at the end of inflation. And gravity waves created during inflation should leave their fingerprint as polarization patterns on the microwave background. This is a subject in the midst of development. Progress is rapid and the stakes are high. But if you think we've reached the end of the story about inflation, think again. Some of its most amazing qualities I haven't yet even mentioned, but I will, of course, in the next lecture.